All right, let's take a look now at section 8.8, talking about improper integrals. Now, when we talk about integrals and integration, we often rely on the fundamental theorem of calculus, which says that if we can find the antiderivative of a function, then the definite integral can be defined using that antiderivative. As a very quick example of that, if you take the integral from 1 up to 2 of x dx, that's a very simple example. Here, you would, of course, by the fundamental theorem, find the antiderivative, which would be x squared over 2, and evaluate from 1 up to 2. When we say we evaluate from 1 up to 2, we mean use the upper boundary and substitute, minus, we're going to take the lower boundary, and we're going to substitute. And then this would give us 4 over 2, which is 2, minus 1 over 2, which we can then subtract to give us our result. The fundamental theorem is a very powerful tool to help you evaluate definite integrals. But what if the definite integral is not defined at your boundaries? And you say, what do you mean? Well, for example, let's consider, let's use the integral from 0 to 1 of 1 over x to the 5th dx. All right, now this looks just like the problem above, except maybe now you think, oh, well, now you gave us a rational expression, so we're going to have to clean that up a little bit. Sure, we can rewrite that as the integral from 0 to 1 of x to the minus 5 dx. Well, notice that we have a major problem here. This function, regardless of how you want to write it, is undefined at 0. Wait, what? Well, yeah, this function is undefined at 0. You say, so? Well, if it's undefined, then it's meaningless at that point. So how can we integrate that way? If that's not quite a problem for you, consider what the antiderivative of this actually is. That would be x to the minus 4 over 4, or in other words, 1 over 4x to the 4th. And when you go to plug in these numbers, when you plug in the 0, that's undefined as well, which means that the fundamental theorem gives you a non-answer. The expression is undefined. So then how do I do this? Or maybe this is undefined. Maybe this actually is just has no result. It's just like taking the natural logarithm of a negative number, right? It's nonsense to us. Well, not quite. So this does make some kind of sense. At least geometrically, we think it should. Because after all, if I take the graph of 1 over x to the 5th, that is a rational expression. Looks something like this. And there will be a branch down here, but I only care from 0 to 1. Okay, so here's 1, and here's 0. And obviously, this is undefined at 0. So I would have a vertical asymptote. But now, one geometric interpretation of this expression is the area between here and here. Well, now part of me wants to say, oh, well, then, yeah, that's pretty obvious. That's going to be infinite. Because, look, it just goes up and up and up forever. Well, yeah, but notice, here, maybe I can draw this a little bit better. Notice that this curve is asymptotic to the y-axis, which means, yes, it's going to go up forever. But it's also going to start getting skinnier and skinnier. So, in other words, this is going to be infinitely tall, but also infinitely thin. In a manner of speaking, it's going to be infinitely tall, times 0. Infinity times 0, that's also nonsense. So what does that mean? Well, this can't be done. You say, oh, okay, great. That was a very short section. We'll call it a day, and we'll pick up chapter 9 now, right? Well, no, unfortunately, that's not quite right. This can't be done the way it's written. But remember, this is calculus, and calculus is all about approximations. We approximate area with an integral. We approximate the tangent line with a secant line, and everything passes through the limit. The limit is what allows us to make our approximations better and better until they yield a final result. So here, notice this is nonsense from 0 to 1. But if I picked a different number, that would be fine. If instead of saying the integral from 0 to 1, what if I said from 1/2 to 1? You say, well, okay, I could do that because that's defined at both 1/2 and 1. But that wouldn't give me my answer. That would only give me the this answer right here. And that's definitely not what I want. I want it all the way back to 0. Oh, well, you know what? Instead of using a half, what if I use a quarter? Okay, well, that's I guess technically better, but still, that's not right. That's not our answer. Oh, well, what if instead of a quarter, I use an eighth or a 16th or 1 over 32? What if I get this number really, really close to 0? Well, the closer I am to 0, the better this looks. This looks like it is the right answer. Well, yeah, but here, that little space in here will always be there. And I can't make it go away because I can't make this 0. Well, that's true. But I can make this so close to 0 that I can't tell the difference. Or in other words, I can take a limit as this lower bound approaches 0. These are called improper integrals. An improper integral is an integral which we cannot evaluate using the fundamental theorem because either one or both endpoints are undefined. There's a third category where maybe the endpoints are the functions defined at our endpoints, but there's a point somewhere in the middle where it's not defined. In other words, the asymptote isn't on either end, but it's somewhere in the middle. So in a moment, I will introduce the full gambit of those, but for now, let's go ahead and continue this problem. Because here, this technique that we mentioned looks like this. We can take the integral from, now here, I don't want to use 0, but I want to use some number, and that number is going to go to 0. So here, I'm going to use the letter A, because normally that's, from A to B. So here, I'll use the letter A to signify that's my lower bound, and it's not 0, but we're going to make it really close to 0. This upper bound, we can leave it as 1 because after all, we can plug in 1 into this. That's fine. No big deal there. So what I want to do is I don't want to take the integral from 0 to 1 of this. I want to take the integral from A to 1 of this. And this I can do. No problem. Okay, so now the fundamental theorem applies. I can, I can add 1 to the power and divide by the new power. So this will give me x to the minus 4 over minus 4. And then I'm going to evaluate this from A up to 1. Okay, well, I can do that. Look, I can just plug in the number 1 right here. 1 to any power is still 1. Okay. In fact, let me write this way. I'm going to write this as 1 over negative 4 x to the minus 4th. Just like that. Same thing, just brought it. That should be a positive 4. I just brought down my negative power. And again, I'm evaluating from A up to 1. That's not necessary, but it'll make my arithmetic a little bit easier here in just a moment. If I substitute in 1, that's going to be 1 over minus 4 times 1, or in other words, negative 1/4, minus, and now if I substitute an A right here, that's going to be 1 over negative 4a to the 4th. Here, double negative makes that a plus, so we can just write this as, let me write the positive one first. Let me write that as 1 over 4a to the 4th minus 1/4. Okay, very nice. So this integral is given by this antiderivative at these endpoints, which ends up giving me 1 over 4 a to the 4th minus 1/4. Okay, that's fine. But remember, a is some number that is over here. It's positive. It can't be 0. But I wish a was 0. Well, so what? You can wish whatever you like. It can't be 0 because if you substitute in 0 here, for example, that's nonsense. It's gonna be undefined. But you know what I can do? I can take this and take its limit. What I want to do is I want to take the limit as a approaches 0. Now, of course, here I'm approaching from the right-hand side. So that's a approaches 0 from the right. Well, if this integral is equal to that, then the limit of this integral is equal to the limit of that. So this is the limit as a approaches 0 from the right, which is the limit of this one, which is the limit of this one, which is the limit of this one. But now, if this equals this equals this equals this equals this, I can take this limit. Here, that's a constant, which means taking a limit won't affect it. That'll stay 1/4. As a approaches 0, 1 over 4a to the 4th, that's 1 over something that's getting smaller, which ends up giving you something that's infinitely large. So here that's infinite, minus a little bit, well, that's still going to be infinite. If you take something that's infinitely large and subtract a constant, no matter what constant that is, you still end up with something that's infinite. All right, so that looks like this. And you say, well, okay, but I mean, I probably could have guessed that just from the picture. I mean, look, that goes up forever. Of course that's going to be infinite. Well, not necessarily. So that's one example. Let's consider another example. And let's look at the integral from 0 up to 1. Use the same kind of boundaries. And I'm going to go ahead and use 1 over, let's say, x to the, let's say square root of x. Let's try that one. So in fact, you go ahead and give this a try. Go ahead and mirror this procedure. Go ahead and try this right here. You're not going to be able to substitute in 0 because that would make the expression undefined. But you're going to take a limit as this value, we're going to call it a, let that approach 0 from the right. Go ahead and give that a try. Once you get an answer, go ahead and unpause the video and we can go through it together. But go ahead and pause it right now and see what you get. All right, so let's take a look. Oh, and my apologies, I never put a differential in there. All right, so here we say that's the integral from 0 to 1 of 1 over square root of x. Let me rewrite that in a slightly more friendly looking notation. Let's write this as x to the minus 1/2. Okay, something like that. All right, so now I can take this expression and let me, instead of doing this, which is impossible, you can't evaluate at 0 because it's undefined, let's write this as the limit as a approaches 0 from the right of the integral from a to 1 of x to the minus 1/2 dx. Okay, here I can use the fundamental theorem on this part. After all, that's not 0. All right? It almost feels like it's cheating. It's going to be 0, but it's not exactly 0, so we can kind of get away with that. So now, looking at this, we can take this expression and, using the fundamental theorem, because it does apply now, we can add 1 to the power divided by the new power. So I can write this as x to the power, well, let's see, if I add 1 to this, that's power 1/2, and I'm dividing by the new power, which is also power, which is going to be 1/2. And that's evaluated from a up to 1. Here I'm dividing by a fraction. That's the same as multiplying by a reciprocal, so let me write that in a friendlier way. That's 2x to the 1/2 evaluated from a up to 1. And here I'm forgetting my limit, which I should not be doing. So that's the limit as a approaches 0, and here that's the limit as a approaches 0. Okay. So now I can take this and evaluate it from a up to 1. So let's go ahead and do that. We start with 1 and then with a. So this will give us the limit as a approaches 0 from the right of, if I substitute in 1, well, that's just the number 1. 1 to any power is still 1. So that's just going to give me the number 2. Minus, now if I substitute a, that's going to be, well, that's 2a to the 1/2. So I'm just using the fundamental theorem, plugging in my endpoints and subtracting. But now I'm going to take the limit as a approaches 0. Notice, as a approaches 0, this thing just goes away. So here, the limit as a approaches 0, that stays constant, and this drops to 0. So that's 2 minus 0, which gives me 2. If I look at the graph of 1 over the square root of x and 1 over x to the 5th, they do have the same kind of shape. And here we have an illustration. Oop, what just happened? Oh, there we go. It just flipped around. Here we have an illustration which shows us what these graphs look like. This one in sort of a purple color would be the, ignore the real part. This program allows me to graph things in the complex plane as well. Here, this red one would be the graph of y equals 1 over the square root of x, while this one has the graph of y equals 1 over x to the 5th. Notice both of these are asymptotic to the x-axis, as would be implied by their numerator. Notice that also both of them have roughly the same shape, albeit one is clearly different size than the other. So here, even though both of these go off to infinity, here between 0 and 1, I have the amount of area keeps going up but yet one of these has an infinite integral. The result is infinite in size, while the other one was just 2, as we clearly see here. So the concept of area underneath the curve takes on a bit of a strange turn in that here the visual intuition may no longer be sufficient to tell us exactly what's going on. Fortunately, we don't need the visual intuition, although it's nice to have, to work these out. So now let's take a look generally at what we mean by improper integrals. Here we see an example, and this really is the same kind of example for both. But let's talk about generically what these are going to look like. So here we have a definition. Let's let f of x be a function. Now, if f is continuous on an interval from a to b and discontinuous at b, all right, so it's continuous everywhere in this interval, including one endpoint, but it's discontinuous at this endpoint down here, the one on the right-hand side. Then to take the integral from a to b of f of x dx, that's going to be given by the limit as c approaches b from the left from a to c of f of x dx. Or in other words, I can't use b because my function's not continuous or maybe even defined there. So instead, I'll stop just short of getting there. I'll take the integral from a up to c, and c is a little bit before I get to b, and then I let c go to b from the left. On the other hand, if f is continuous on an interval from a to b, everywhere inside of a and b, including b, but not a, and here it's discontinuous at a, then the integral from a to b of f of x dx is equal to, well, you don't go all the way to a. You take the integral starting from just a little bit after a, the integral from c to b of f of x dx, and then you let c approach that number where your function was undefined. All right, that's what we have over here. That was our case, or our two cases. Both of them were like that. Notice we couldn't evaluate at 0, so instead we evaluated it at some arbitrary number a, and then let a approach 0. Here we evaluated it at some arbitrary number, and then we let that number approach the value that we really wanted. And finally, here we have if f is continuous on an interval from a to b except for some c in the open interval from a to b, or in other words, okay, let's say it's continuous all the way from one endpoint to the other, but except for one place, which happens to be in the middle, not the left side or the right side. I said that backwards. Not the left side or the right side, but somewhere in between. Well, then what you're going to do is you're going to split the integral into two integrals, where the upper bound of one integral is the discontinuity. The lower bound of the second integral is, again, that same discontinuity. And then you're going to evaluate both of these as if they were either of the first two cases. So really, this is a combination of both of these. If these kinds of improper integrals, these kinds of improper integrals converge if the limits exist. So if this limit gives me a value, then this converges. Same thing here. If this gives me 2 or 1/3 or whatever, then the integral converges. But if it doesn't, if this is infinite, if this does not exist, then the integral is said to diverge. All right? So let's take a look at some more examples of this. All right, let's go ahead and consider a function which looks like 1 over the cube root, that should be cube root of x minus 1. Okay, now this function is clearly undefined at the value 1. So here you have a nice asymptote right in there, which means that if we were to integrate from 1 to 2 or from 0 to 1, you would certainly have a problem. Well, here what we're going to do is we're going to integrate all the way through. We're going to start from 0 and we're going to go out to 3. All right, so let's take a look at how this is going to work. So let's integrate this from 0 up to 3. All right, so once again, this is undefined when x is equal to 1. And so because 1 is in this interval, as it's currently written. But of course, we do have this here, which states that if you have a discontinuity somewhere in between the two extremes of your interval, you can split that integral into two separate pieces. All right, so let's go ahead and do that. Here, the discontinuity is at 1, which means I can write this as the integral from 0 to 1 of 1 over the cube root of x minus 1 dx plus the integral from 1 up to 3 of 1 over the cube root of x minus 1 dx. Just like that. Now, each of these fits one of these two categories from before, where either the function is discontinuous at the right endpoint or it's discontinuous at the left endpoint. Right? So here we can go ahead and establish these two integrals by writing them as limits as you approach your two endpoints. So here this is going to be equal to the limit as is to be 1 because that's undefined. So we're going to write this as the integral from 0 up to b. And here we want b to approach 1. Now it's going to be less than 1 because it's somewhere between 0 and 1. So we're going to approach it from the left. That will make a difference if these are signed values, and especially with radicals, sometimes the signs do make a difference. So do make sure you pay attention to which side you're approaching from. Many times this won't make a difference, and it won't make a difference until it does. So make sure you watch that. And that's going to be the limit of the integral from 0 to b of, and now this remains the same, that's 1 over the cube root of x minus 1 dx. Plus the, and now here we want to take this lower bound and we want to make sure that it's not 1, it's some number that's, you know, bigger than 1. But then we want to take the limit as that number approaches 1. Now, it's a little bit bigger, so it's going to approach from the right. And now we can evaluate. Note that for this integral to exist, both of these limits must exist. If this gives you 2/3 and this gives you infinity, well then that still diverges. For this to converge, both of these must converge. If one diverges, that's enough. The whole thing diverges. If they both diverge, well then it definitely diverges. All right? So let's go ahead and take a look here. This is going to give us, we need to take the antiderivative because after all, now the fundamental theorem does apply. All right, so let's see. That's, well, let me do that off to the side here a bit. If I want to take the antiderivative of 1 over the cube root of x minus 1, and let me do that off to the side. That's the same as taking the antiderivative of x minus 1 to the minus 1/3. Right, cube root and the denominator minus 1/3. And now here I can go ahead and use the power rule. Oops, forgetting my differential. So now that's going to be, I can add 1 to the power, so that's x minus 1 to the 2/3. Now I divide by the 2/3, which is the same as multiplying by 3/2. All right, plus a constant of integration. Now here, because of the chain rule, I should now divide by the derivative of this part, well, the derivative of this part is 1, so that remains completely unchanged. So if that's my antiderivative, I can now go ahead and say this is equal to the limit, and that's a little side work there. That's the limit as b approaches 1 from the left of 3 times x minus 1 to the 2/3 over 2. Here we don't need a constant of integration because this is a definite integral and the constant will go away in a moment anyway. So this is from 0 up to b. Separately, this is still the same antiderivative, but now we're going to take the limit as a approaches 1 from the right of, that's 3 times x minus 1 to the 2/3 over 2. And now we can go ahead and evaluate that at its endpoints, which are a and 3. Okay, so now this is going to be the limit as b approaches 1 from the left. Notice I have not evaluated my limit yet, so that's coming along for the ride. That's the limit as b approaches 1 from the left of. If I substitute in b right here, that's going to be 3 times b minus 1 to the 2/3 power over 2 minus, if I substitute in 0 right here, well, okay, that's just a constant. 0 minus 1 is 1. Oh, sorry, 0 minus 1 is negative 1. Negative 1 to the 2/3 power times 3 over 2. So now, negative 1 to the 2/3 power over 2. Which incidentally, fun little quirk. You got to be careful with some of this arithmetic. We're starting to look at things which can take on some complicated forms. This number right here, depending on how you treat it, is a complex number. The strange thing about this is, depending on what calculator you're using, if you happen to be using one of those, it may be undefined. Here, if I take negative 1 and raise that, if I take negative 1 and raise that to the 2/3 power, my calculator says that's undefined. I'm not sure. You might try your calculator and it might give you something different. Of course, we know this is defined, right? We can write this as negative 1 squared to the 1/3 power, which is 1 to the 1/3 power, which is just the number 1. So we know this is the number 1, but just be mindful of the fact, starting in this section and sort of going forward, a lot of these numbers can take on some complex forms, literally as in complex numbers, and your technology may not be well suited to evaluate this. Or maybe it is, but just be careful with that. Here, we can say this is the limit as a approaches 1 from the right of, and here we're evaluating this at the endpoints and subtracting. So that'll be 3 times 3 minus 1, that'll give me 2 to the 2/3 power. And that one will be fine in any calculator, any modern calculator, over 2 minus 3 times a minus 1 to the 2/3 power over 2. All right. So now we can simplify some of these numbers here, but well, here, let's just consider the limits. As b approaches 1 from the left, all right, well then this expression here is approaching 0, because after all, if you're approaching 1 minus 1, that's going to approach 0. Now, does that negative make a difference? Does that, well, not in this case, because if you approach 1 from the left, that would be something like 0.9 or 0.99. If you take that and subtract 1, you're going to get a very small negative number, something like 0.1 or 0.001, or something along those lines. But if you raise that to the 2/3 power, the square here will make that a positive, and then the cube root will keep it positive. So here, the negative won't make a difference for this particular problem. So here, this does drop down to 0. So we can say this by taking the limit, that does go to 0. Same thing here, this part, as you approach 1 from the right, now this is strictly positive because you're approaching 1 from the right. That's something like 1.1 or 1.01. If you subtract that away, that's a very small positive number. And then if you raise that to the 2/3 power, it's still a small positive number. So here, this goes to 0, which means this entire expression goes to 0. Oops, 0. And now, all that's left are my constants. So I can write this as, all right, so that's going to be, that's a 1. So that's negative 3 times 1 over 2. That's negative 3 halves plus, and this is a constant. It's not a very nice looking constant, but it's 3 times 2 to the 2/3 over 2. And if you like, I'm sure you can write this all number of ways. 3 halves is the common factor. And here you could write this as 2 to the 2/3 minus 1. Either of these would be fine. So this gives us our result. And we note that our integral, even though it has a asymptote in the middle, it has an infinite discontinuity. Given our definition of that kind of integral, we can still evaluate it. We can separate it into 2 separate pieces, and because the limits do all exist, that means that this integral does in fact converge. And not only do we know that it converges, we know what it converges to. Or in other words, we know this is equal to this. So our integral converges. That was an example. All right, now, whenever you're looking at these types of integrals, the improper integrals, these are not always going to have constant boundaries. In the three cases we've seen, we've had constant boundaries where either you have a problem at the right boundary, at the left boundary, or somewhere in between the boundaries, which in reality is just a combination of the previous two. But we can also have a different kind of improper integral. Consider the following definition. So let's begin with a function f. Let's say f is continuous on an interval that has no endpoint on one side. Let's say it's continuous on the interval from a to infinity. It is continuous and defined at a, but obviously you can't define a function at infinity. Here, that's not a number. So what does it mean to have the integral from a to infinity of f of x dx? Well, what that means is I want the limit as b approaches infinity. Just like before, I can't actually plug in that number. My function is not defined at infinity. That's nonsensical. We don't know what that means. Functions are defined at numbers, at values. So it doesn't make any sense to be defined at infinity. No, but it makes sense to be defined at b. We know what it means for a function to be defined from a to b, regardless of what these are. And once you can figure that out, then you can take the limit as b approaches infinity, and that defines how we take this kind of integral. This is another form of improper integral. Your function doesn't have to be going off to infinity to the right. It can do so to the left. We can take a function continuous from negative infinity to b. It's defined and continuous at b, but not as you go off to negative infinity. So the definite integral from minus infinity to b of f of x dx, we're going to define that as being the limit as you go from a to b of f of x dx, and you allow a to approach negative infinity. In other words, here, have normal, regular boundaries, the kind you could take advantage of using the fundamental theorem, and then let your normal everyday limit approach the infinite value that you want. And if your function is continuous on both sides like this, to infinity on both sides, right? Then to define the definite integral from minus infinity to infinity, that's equal to the integral from minus infinity to c plus the integral from c to infinity. Or, in other words, you go ahead and split it in half. You say it's continuous forever to both sides, I'll split it somewhere. And that way, one part of your integral looks like the first case, where it's defined from some number forward, and the second part of your integral looks like one of these second improper integrals, where it's defined from some number backwards, So let's consider now an example of this type of indefinite integral, this type of improper integral. So let's consider this function here, which is going to be given by 6 over x to the 4th power. Notice here this has, all sorts of problems. Here, this is, in fact, defined from negative infinity to infinity. You can substitute in any value you like, except it's not defined at 0. So this presents all kinds of problems. If we wanted to take an integral from minus 4 to 4, that would pose a problem at 0. If we want to take an integral from 0 to 2, well, again, you'd have a problem at 0, or from negative 6 to 2. But here, we're not going to consider that kind of problem. What we're going to look at is we're going to look at the integral from 1 to infinity. Notice that avoids this problem. We don't have an issue at 0. It's not a big deal because we are not considering 0 either as the endpoint of our integral or a point inside of our integral. And here is the offensive problem. So note that 0 would be a problem, but it's not in consideration here. It's not our endpoint, nor is it in between our endpoints. Now here the issue is the fact that one of our boundaries is infinite. So we can go ahead and define this as, instead of the integral from 1 to infinity, which is nonsense, how do you substitute in an infinite value? You would instead take the integral from 1 up to b of 6 over x to the 4th dx. And once you found that, then you could extend this value b as high as you wanted. So here we would take it and extend b to infinity. Here we don't have to worry about left or right because there's only one way to approach infinity. So, well, for our purposes, yeah. So here we can go ahead and use the fundamental theorem on this part, and that tells us that we can take an antiderivative and then evaluate it at the endpoints. So here, just for my convenience, I can write this as the limit as b approaches infinity of the integral from 1 to b of 6x to the minus 4th dx. Because even after all these years, rational functions seem complicated, but the power rule is just a much simpler thing to remember how to use. So here, I can add 1 to this power and divide by the new power. So this will give me the limit as b approaches infinity of 6x to the minus 3rd divided by a minus 3rd, evaluated from 1 up to b. Okay. Now here we're taking an integral from 1 to infinity. That does go on forever to the right. But we also saw in the graph that the function really quickly goes toward the asymptote. So the height of your function reaches what's essentially 0, but the width is essentially infinite. Infinity times 0. I don't know what that means. Well, this will tell us what it means. Here, let's go ahead and simplify just a bit. These two divide out. So I can write this as the limit as b approaches infinity of minus 2x to the minus 3 from 1 to b. Or maybe I should write that as the limit as b approaches infinity of minus 2 over x to the 3rd. All of these mean the same thing. So now, let me evaluate at x is equal to b. All right, well, that's going to give me the limit as b approaches infinity. Notice we haven't used our limit yet, so it's coming with us every step of the way. And that's going to be negative 2 over b to the 3rd power minus, and that's going to be negative 2 over 1. Okay, well, that's just negative 2. And now here, that's going to be negative 2 over b to the 3rd. But as b approaches infinity, this denominator becomes infinitely large. But if you remember from Cal 1, the limit of a constant over a power of x, or in this case a power of b, as b approaches infinity, that's going to go to 0. So here this expression is just 0 as you take its limit. And here this expression is constant, so it's unaffected by a limit. So here you're left with 0 minus a minus 2, or in other words, you get 2. And there we go. Here you can take the integral from 1 to infinity of 6 over x to the 4th dx, and you, in fact, have a convergent integral. It converges to the number 2. This is an example of this first case from 0 up to b. Right? From a up to b. From a to infinity, okay, let b approach infinity. From a to infinity, okay, do it from a up to b and let b approach infinity. Let's consider another example. Let's say we want the integral, and now let's make it from minus infinity to infinity of 8 over x squared plus 4 dx. This type of function, by the way, has a special place in mathematics. It's one that looks like this, often called a bell curve, a little more formally called a Gaussian curve, and it's one that's studied in probability and statistics, along with other things. The name of this kind of curve, if you're talking probability and statistics, it's like I said, a Gaussian or a bell curve, or some modification thereof. But in analysis, this goes by another name, the witch of Agnesi. Now, you might think you heard me wrong or the video is glitching or something, but no. That is called the witch of Agnesi. Before we get into the math of this is just one of those strange quirks of history and a strange little quirk of math. The name of this kind of function, a constant over the sum of squares, where you have a variable and a constant squared. This is called the witch of Agnesi. It is a joke that goes back hundreds of years. The Agnesi was Maria Agnesi. She was a mathematician who studied probability statistics and what is now considered just normal statistics. But at the time, her work was being collaborated with other mathematicians around the world. So one of the things that had to happen was a translation. You have to translate work from one language to another. In one of her works, she refers to a curve, and it wasn't anything particularly special to her or anything that she invented. Rather, this was a curve that she had been studying in depth. And she described it as aversera, and I'm sure I'm mispronouncing that, but it literally means a turn, or if you take it a little more loosely, it means a curve, because of course that's what she was studying. She was studying this kind of a curve. But the person who was translating it was not a mathematician, and in fact had no mathematical background at all. So they saw this word and thought, oh, it must be misspelled. The only word that I know of that looks like this is this word. And aversiera, which they thought, oh, that must be right. They must have just switched the I and the S. This means a demon. But, well, now, demon is, this was in Latin, and Latin, like Spanish or French, is a gendered language. There's a difference between male and female pronouns. So ending with an A, it would be a female demon. So the translator wrote that down and thought, that just sounds strange, a female demon. Well, another name for a female demon is a witch. At least that's what they thought. And so when the translation came out from the Latin into, I believe, the French, the notation that Agnesi had put on her paper said, "Oh, this is the curve that we'll be studying." It read as, "This is the witch that we're interested in." And the name stuck. It is a joke about a mistranslation that goes back a few hundred years now. So in any event, looking at this, the witch of Agnesi, which these types of curves are called, is one of interest in several branches of mathematics, and particularly statistics and probability. Here, let's take a look at its integral from minus infinity to infinity. Now, as we saw the picture just a moment ago, it's a bell curve, and it goes off forever in both directions. So, well, let's see. It is possible, of course, to have an infinite integral and have it converge to just a number, but maybe it doesn't. So here, let's find out. Notice this has both endpoints being infinite. So here we want to split this. We don't want to write this as a single integral. We want to write this as the integral from minus infinity up to, and here we're just going to pick some point between minus infinity and infinity. You can pick literally anything, because of course this is defined for all real numbers. So you could pick negative 10 or pi or 76. I like 0. 0 is a nice, simple number for me to work with. And here, that's going to be wherever this one stops, that's where the other one picks up. And there we go. So now go ahead and pause the video and give this a try. This will work exactly like the one above it. This will look just like this. Now, it probably won't equal to the number 2, although it might, but the setup is the same. And then try this one. Note that the limit is defined for the upper bound, but not for the lower bound. So here, the lower bound is the one that you need to substitute. So pause the video, give it a try, and when you get an answer, go ahead and unpause, and we'll go through it together. All right, so let's go ahead and finish this off. Here, we can write this as the integral from a to 0, and here let me make my a little more pronounced, of 8 over x squared plus 4 dx. And here we want this a to eventually approach minus infinity. So let's take the limit as a approaches minus infinity. Plus the integral from, let's see, what would that be? From 0 up to some arbitrary constant. And then, of course, we're going to want that arbitrary constant to approach 0. So the limit as b approach, oh, sorry, not 0, infinity of 8 over x squared plus 4 dx. So now we're going to go ahead and use the fundamental theorem. We can find the antiderivatives of these and then evaluate at the endpoints and take a limit. Here, the antiderivatives of these are an arctangent. Go ahead and recall from a previous section that if you have the integral of 1 over x squared plus a squared dx, that's going to equal to the 1 over a times the arctangent, the inverse tangent, of x over a, plus a constant of integration. And of course, here we won't use the constant because this is a definite integral. But here, this is the antiderivative. So here, this 8 is a constant. It won't bother us. So here we can write that the, let's see here. We can write that the limit, let's not get to the limit just yet. We can write that the integral of 8 over x squared plus 4, which is really 2 squared, is going to equal to, dx, is going to equal to 8 times, here the 8's a constant, just factor that out, is going to equal to 8 times 1 over 2 times the arctangent of x over 2, plus a constant. And so the antiderivative of 8 over x squared plus 2 squared is, here this will give me 4 times the arctangent of x over 2 plus a constant of integration. So if that's our antiderivative, we can use the fundamental theorem up here with that. So this will be equal to the limit as a approaches negative infinity of, well, we know our antiderivative. It's going to be 4 times the arctangent of x over 2. We don't need that plus c. This is a definite integral, so that constant would subtract away. And this is from a up to 0. Plus, we're going to take the limit as b approaches positive infinity. And again, we have our antiderivative. So that's going to be 4 inverse tangent of x over 2 from 0 up to b, just like that. We can evaluate these at the endpoints. So this will give me the limit as a approaches minus infinity. If I evaluate this at 0, the inverse tangent of 0 is 0, I believe, yes? So that's going to give me 0. So let me not worry about that. Minus 4 times the inverse tangent of a over 2. Plus, here, if I plug in b, that'll give me, I still want to take the limit. The limit as b approaches infinity of 4 times the inverse tangent of, let's see, that would be b over 2. And if I plug in 0, the arctangent of 0 is 0. So I could say minus 0, but that makes no difference. So here we are. Now at this point you might say, well, wait a minute. How do I evaluate that limit? I'm used to polynomials and rational expressions, even trig functions, but what about arc functions? I don't remember that. Well, then it'll help to remember what the graph of the arctangent looks like. So are y'all thinking about that? Visualize, what is the graph of the arctangent function? Okay, once you visualize that, what happens to the arctangent function as the argument goes to infinity? Separately, that same function, that same graph you're visualizing, what is going to happen as your argument goes to negative infinity? Right? Think about that for a minute. Pause the video if you have to. Try to draw it out. evaluate. Once you have an answer, go ahead and unpause the video and we'll go through that together. And in fact, here's the graph. So here's the arctangent function, thinking back to trigonometry. For those of you who don't remember that, shame on you, trigonometry. And remember that the arctangent function has a couple of horizontal asymptotes. One of the horizontal asymptotes of the arctangent function is pi over 2. The other horizontal asymptote of the arctangent function is negative pi over 2, which means that as x approaches infinity, as the argument approaches infinity, the inverse tangent will approach pi over 2. But as your argument approaches negative infinity, as the x approaches negative infinity, that means that your functions will converge to negative pi over 2. It'll approach negative pi over 2 as its asymptote. So, as you approach infinity, the arctangent of b over 2, well, that's going to approach infinity also. But we just saw that as your argument approaches infinity, the arctangent will approach pi over 2. So that's 4 times our pi over 2. Right. And then over here, that's going to be negative 4 times. And we saw that as a approaches negative infinity, well, that's going to approach negative infinity. But the arctangent, as you approach negative infinity, is negative pi over 2. So that's going to give me positive 2 pi. And that's also going to give me positive 2 pi. So if you take the integral from minus infinity to infinity of 8 over x squared plus 4 dx, you get 4 pi. And yes, I did just hesitate to do that. All this other stuff I can do automatically, but I swear 2 plus 2 gives me 4. I actually had to stop and think about that for a second. So that is our result. Finally, for this section, we have one more kind of integral that we want to look at. For right now, it's just a special case, but in later sections, this will turn out to be extremely useful. So here, this is a theorem. All right? So if you have an integral from 1 to infinity of dx over x to the power p. Here, you're not told what p is equal to. It's just some number. But depending on what that number is, you're going to get a particular answer. So here, if p is greater than 1, then this will converge to 1 over p minus 1. And that is if your p is greater than 1. On the other hand, it just outright diverges. It fails to give you an answer if p is less than or equal to 1. Just like that. Once again, for now, this is a theorem. Here's something we're going to go ahead and prove. But in later sections, this will turn out to be rather useful. So let's talk about the proof. The proof of this is completely accessible to us because, of course, it is constructive. We're going to construct an answer and see what happens. So here we don't know what p is, nor does it really, really matter for the time being. So here, all we're going to do is we're going to compute this integral. We're going to say take the integral from 1 to infinity. And for some reason that looks like a 0. There you go. From 1 to infinity of dx over x to the p, which is, here I'm going to write this a little bit more, in a little bit more of a friendly way. I'm going to write this as x to the minus p dx. That'll help us out in a moment. All right, well, we've seen how to evaluate something like this. We're going to evaluate it as a limit. Okay, so this is the limit as, that's our upper bound, so I'll call it b, as b approaches infinity of the integral from 1 to b of x to the minus p dx. Okay. Now, anyone who's feeling brave, go ahead and pause the video and see how far you can get on this. Go ahead and evaluate the limit. You should be able to do that part. And then once you've evaluated the limit, see what you can do in terms of this. Once you have gotten to a part where you think you've finished, go ahead and unpause the video and we can go through that together. All right, so let's go ahead and take our integral. Here that uses nothing more than the power rule. We're going to add 1 to the power and divide by the new power. So here that's going to equal to the limit as b approaches infinity of, now here I'm taking the antiderivative, so that's going to be x to the minus p plus 1, and then I'm dividing by the new power, which is minus p plus 1, and that's being evaluated from 1 up to b. Now here, I'm going to write negative p plus 1. I'm going to write it the other way around. Let me write this as the limit as b approaches infinity of x to the 1 minus p over 1 minus, that's right, 1 minus p. All right. Okay, so now that's going to be evaluated from 1 up to b. Okay, so now this looks a little confusing. Sometimes it's hard to keep track. Wait, what am I plugging into? Remember, these are with respect to with respect to x. Because after all, you integrated with respect to x. So x is your variable, right? P is just some number. It's a constant. So don't plug these numbers in for p. You're plugging in for x. So this will give you the limit as b approaches infinity of, let's see here, that's going to be b to the 1 minus p over 1 minus p minus, and now I'm going to plug in the number 1, which is 1 over 1 minus p over 1 minus p. Right? Here, 1 to any power is 1. It doesn't matter what this power is. So here, let me write this in a somewhat friendlier way. Let me not use powers that I don't need. So that's the limit as b approaches infinity of b to the 1 minus p over 1 minus p minus 1 over 1 minus p. Right. And here, let me go ahead and do one other thing. Let me go ahead and rewrite this in a slightly different way. Note, I can write, let's do that right up here. So note, I can write negative 1 over 1 minus p, that's what I have here, negative 1 over 1 minus p, as being 1 over p minus 1. Oop, seems to have disappeared there. Just like that. Here, note that all I've done is I've multiplied the top and bottom by negative 1. If I multiply the top by negative 1 times negative 1 is positive 1. If I multiply the bottom by negative 1, that negative p becomes a positive. That positive 1 becomes a negative. So here I can, instead of writing this as minus 1 over 1 minus p, I could write it as plus 1 over p minus 1. Oh, that looks like that's going to be useful, isn't it? So here that's going to be equal to the limit as b approaches infinity of b to the 1 minus p over 1 minus p plus 1 over p minus 1. Just like that. So now we say, well, let's go ahead and take the limit now. Well, it sort of depends on what p is. Let's separate this into a few different cases. First of all, case number 1. What happens if p is equal to 1? Well, then my limit becomes the limit as b approaches infinity of b to the 1, now p is equal to 1 there, yeah? So 1 minus 1 over 1 minus 1 plus 1 over 1 minus 1. All my p's have been replaced by 1s. Oh, but that's nonsense. That's the limit as b approaches infinity of, well, that's 2 over 0. Oh, that's nonsense. This is undefined. Oh, okay, so then that means p cannot equal to 1. If p equals to 1, it'll diverge. So the integral diverges when p equals to 1. Oh, well, that's part of our theorem here. It diverges if p is equal to 1. Well, what if p is not equal to 1? Well, then it's either greater than 1 or less than 1. Let's see here. Case number 2. Let's say that if p is, let's go with less than 1. All right. Well, if p is less than 1, then this right here, 1 minus p. Well, if p is less than 1, then this is positive. If p is less than 1, then 1 minus p is greater than 0. If you take 1 and subtract the number that's less than 1, if you take 1 and subtract the half, well, that's a positive. It doesn't matter what it is, just it's a positive. Oh, okay, well, if that's a positive, then here, that's going to stay in part of the numerator. If it was a negative, it would come down to the denominator, but here, this stays as part of the numerator. So, I'm going to have my limit as b approaches infinity of b to the 1 minus p over 1 minus p plus 1 over p minus 1, like that. Here, this is constant. Notice it doesn't have a b, so that's a constant number. Okay, so what about this thing? Right here, this is constant. Well, if this is a positive number, then here I have something that's infinite being raised to a power. Well, that's going to be infinite. And if I have something that's infinite, remember, this is just a regular number, right? This is p is a constant. 1 minus p is also a constant. So this is infinitely big divided by a constant. Oh, that's going to be infinitely big. And if you have something that's infinitely big and you add 5 or something, well, that's still infinitely big. So here, this diverges. This is infinite. This goes to infinity. And remember that if the limit goes to infinity, that means that the limit does not exist because it's infinite. For a limit to exist, it's equal to a number, a constant number, finite constant number. So that means the integral diverges when p is less than 1. Okay, and then, well, we know what happens when p is equal to 1. We know what happens when p is less than 1. What about when p is greater than 1? Well, that's our third case. Case number 3. And that's what happens if p is greater than 1. Well, if p is greater than 1, then 1 minus p is going to be negative, right? Because if you have a number that's greater than 1, say for example 2, 1 minus 2 would be negative 1. If you're subtracting a number that's bigger than 1, you're going to end up with a negative. Okay, but since that's a negative, that means it's going to come down into the denominator. So here we can write this as the limit as b approaches infinity of b to the 1 minus p over 1 minus p plus 1 over p minus 1. Since this is negative, we could bring it down into the denominator by making it a positive. Oh, in other words, by changing its sign. So this is equal to the limit as b approaches infinity of 1 over 1 minus p times, and now this thing came down to the denominator. Here, that's going to be p minus 1, like that, right? When you bring it down, you switch its sign. And now you're going to add 1 over p minus 1. Right? We rewrote this because it had a negative power, and this is a constant, so we leave it alone. Okay, but now this had a negative power, which means down here it has a positive power. 1 minus p is negative. P minus 1 is positive. So now you have something that's infinite to a positive power that's infinite. But that's in the denominator of a fraction with a numerator that's constant. 1 over something that's infinitely large, that's going to go to 0. So here, just this part right here is going to be infinite, which means the entire thing is 0. 1 over something that's infinite is going to give me 0. Okay, so that goes away, and I am just left with 0 plus 1 over p minus 1, which is 1 over p minus 1. Oh, but that's a number, right? Because p is a constant. P is some number. We don't know exactly what it is, but it's a number. So 1 over P minus 1 is also a number. So if P is greater than 1, the integral, well, it's equal to a number. That means it converges. And not only does it converge, but we know what it converges to. We found that the answer is 1 over P minus 1. Okay, so there's three possibilities. If P is equal to 1, or if P is less than 1, well, then the whole thing diverges. Oh, if P is less than or equal to 1, the whole thing diverges. Oh, but if it turns out that if P is greater than 1, then the integral converges. And not only does it converge, we know it converges to 1 over P minus 1. Okay, so if P is greater than 1, then the whole integral converges to 1 over P minus 1. And that proves our result. Which is nice. Here, this can give you a nice shortcut for a particular kind of integral. It's not an integral that appears very often in practice. However, in the next few sections, it'll be a nice shortcut for a particular kind of convergence test. For a particular what now? Well, we'll talk about those when we get to the next few sections. But here, let's just take an example of using this very, very quickly. Here, if I take the integral from 1 to infinity of, let's say, dx over x to, oh, I've gone out of focus there. Okay, there we go. The integral from 1 to infinity of dx over x to the power, let's say, power 5, that's going to equal to, well, first of all, here we know that the power 5, that's greater than 1. Okay, so here this will converge to, and not only do we know it converges, well, we know it converges to 1 over P minus 1. Oh yeah, but P is the number 5. So that's going to converge to 1 over 5 minus 1, or in other words, it'll converge to 1/4. If we want to take the integral from 1 to infinity of dx over, let's say, the square root of x, that's the same thing as the integral from 1 to infinity of dx over x to the 1/2, like that. Well, that's the same kind of thing. But now our power in our denominator, our value of p, that's 1/2, which means it's less than or equal to 1. Oh, so this diverges. Since p is equal to 1/2, which is less than 1, here the integral diverges. You might say that seems really, really, really limited. I mean, it has to be specifically from 1 to infinity. Well, yes, but you can get clever with it. For example, you might say, I want to find the integral from, let's say from, oh, I don't know, let's say from 5 to infinity of dx over x to the 3rd power. You say, oh, well, that's not going to work. It's not from 1 to infinity. Well, no, it's not. But you know what? If I were to add the integral from, oh, so here, let me not write that way. So here's the question that I want. Okay, so now you say, well, I really don't want this, right? Because that doesn't allow me to use my shortcut. Here, I really wish it was the integral from 1 to infinity of dx over x to the 3rd. Okay, but this can be thought of as the integral from 1 to 5 of dx times x to the 3rd, or sorry, over x to the 3rd, plus the integral from 5 to infinity of dx x to the 3rd. Right? Because after all, from 1 to 5, from 5 to infinity, that covers everything from 1 to infinity. This integral is equal to this one plus that one. Well, that's the one I want. Okay, so let me get rid of this one then. Let me subtract that over to the other side. So that means that the integral from 5 to infinity dx over x to the 3rd is equal to the integral from 1 to infinity dx over x to the 3rd minus integral from 1 to 5 dx over x to the third. But now that one I can do using my shortcut, and that one doesn't have any problems. My function is defined at both endpoints. There's nothing between 1 and 5 where this is undefined. This just uses the regular old fundamental theorem without any of the improper integral nonsense that's made everything so complicated. So here, we can just do each of these on their own. This one, I can use my shortcut. Here, my power of p is 3. So here, this one will converge to 1 over p minus 1, which is just a half. And now I just have to find this one and subtract it. So here, that's minus. And now this just uses the regular old fundamental theorem. If I take the antiderivative of dx over x to the third, I'm going to get 1 over negative 2x squared, evaluated from 1 up to 5. Let's see here. So that's going to be minus. And here, let me just do this part on its own. If I evaluate here at 5, that's going to give me 1 over, let's see, 5 squared is 25, times negative 2 is negative 50. If I evaluate at 1, that's going to be 1 over negative 2 times 1. That's going to be, so minus 1 over negative 2, just like that. Let's see here. That's going to give me 1/2 minus, let's see here. If I say minus a minus, that makes this a positive. So that is simply 1/2 minus 1 over negative 50. So here, double negative makes that a positive 1/2. And then that's a negative, so I can say minus 1 over 50, like that. And now here, you say, okay, find a common denominator. No, look, 1/2 minus 1/2. That's gone. Minus a minus, that's a positive. Okay, so that's going to be positive 1 over 50. So here, this theorem that we see is a little bit more flexible than it might initially appear. Yeah, if the integral is from 1 to infinity, okay, just there we go. Since p is equal to 1/2, which is less than 1, the interval diverges. If the interval is greater than 1, then we have a nice result. But even if it's not from 1 to infinity, here you can write it as the integral from 1 to infinity minus something that's easy to find. So you take your shortcut to find this part, and you can find this part manually and get your answer. So that's going to be 1 over 50. So that is it for section 8.8, and that's the end of chapter 8. As a bit of practice for this section, you should try the following problems. This is section 8.8. Go and try problems 17 through 47 odd, and also go ahead and try number 65. If anybody has any questions, comments, or problems, make sure that you can visit the online office hours or our a bit of time during our class, or if you can't make any of that, then an email would be a good idea. It is difficult to explain math by text, by email, but we can give it a try. If you have any questions, please let me know, and I'll do my best to answer in whichever form is best suited. I hope you all have a good evening.